Welcome, viewer. In this video, I will teach you how to get direct control over every pixel on screen without any other tools or libraries than the Windows API and the C or C++ compiler of your choice. If you are anxious to get going, you'll find a link to a text file with all of the needed code in the description. This tutorial is for the beginner C or C++ programmer who knows the minimal basics of the language, but who has never set up a window program and who wants to start working with graphics via bitmaps. You can skip forward to the technical bits via the timestamps in the description. But if you want to know a little bit more about the reasons for this video and what to expect with regards to performance, keep listening. 6 years ago, I was in my mid-30s and had just started programming. After a few weeks of writing text-based programs, I wanted to try working with graphics. This turned out to be more difficult than I had imagined, and it took me over a week of intense research to find even a bare-bones solution of my own. The solution I came up with then was far from as good as the one I use now, but at least I could put colors on screen. While Googling the subject then, I ran into many references to graphics APIs like OpenGL, for example, but that just seemed overwhelming at my level of skill and knowledge. At that moment, I told myself that once I felt ready, I would make a tutorial aimed at beginners in the same situation. Now, that time is finally here. Now, as long as we're working through an operating system like Windows, there are some hoops we have to jump through to work with graphics. But I have tried to distill it to a digestible amount and will lead you through them all. A little disclaimer here about performance. If you want fast graphics, such as in pretty much anything from the last 25 years, you want to learn how to work with a graphics API like OpenGL, DirectX, Vulkan, or some other. That will allow you to make use of the graphics processing unit, or GPU, and that is referred to as hardware rendering. What I will teach you here happens almost entirely on the CPU, the central processing unit, and is referred to as software rendering. That said, you can still do a lot with this method. The game you see running here is one that I am currently working on. It is called Warlock's Gauntlet, and it runs on the same fundamental code that I will share with you in this video. For the record, I am not an expert. I have programmed in C++ for 6 years and am on my 3rd year of computer science studies at university. There might very well be other, better solutions to this problem out there, but this is the best I can do at this time, and I would have found this immensely helpful when I started out. Now, let's get going. I don't know which programming environment you're working in, but I will be working in Microsoft Visual Studio. And so I will just show you how to set up a program from the start in that environment. Once we start it up, we get the option to create a new project, which we will choose. And you should select C++ for your language, even if you want to program in C, and Windows and Desktop. You will select the Windows Desktop Wizard template and click Next. You will give it a name, whatever you want, and then you will create that. This little pop-up window will allow you to fill in the box called Empty Project, which we will do this time. That will allow us to fill in everything ourselves. Click OK. This is the basic view in Microsoft Visual Studio. And here you have your project with some folders, but they are all empty. We want to put a file in the source files folder. Right-click on it and select Add New Item. And here, choose C++ file. Down here, you can select what you want to call it. for now, I'll just allow it to be named source. If you want to program in C rather than C++, you simply make the suffix, the file suffix, .c instead of .cpp. The compiler will recognize this and compile it as C if the suffix is just C, or C++ if the suffix is CPP. Add that, and open the file. That's it for the intro. I'll now jump to a different file, different project that I created beforehand, and take you through that. So here we are in my tutorial program. On the left here is the code that we will soon be going through. We will zoom in for that, but I wanted to start in this zoomed out view just to show you how little code is necessary for creating a window. It's 53 lines, including some comments and spaces. But first, I'd also like to just expand on the suffix concept from before. You see that this file is a .cpp file, so it's a C++ program, denoted by this double plus icon to the left of the file. Now, if I rename it to .c, then the icon changes to a C, denoting it will now be interpreted as a C program by the compiler. I have run this code in both C and C++, and indeed my C and C++ programs both use this fundamental code, so it is a valid program in both languages. I'd like to reiterate that I'm not an expert when it comes to the Windows API or programming for Windows in general, so I'll limit myself to talking about those things that I know anything about and trying to point you in the direction of more information when I can. I might get some things wrong, but the gist of it should be correct at least. First, we include the windows.h library file, which declares a large part, if not all, of the Windows API. This is what allows us to use Windows functions. Then we declare a function called windowproc, or stands for window procedure. This is one that we will define later down here, but we need to declare it here because we will reference it in this part. The next thing is WinMain, which is very similar to the main function of a regular C or C++ program. The difference is that WinMain tells Windows that this is going to be a windowed program. As far as I know, you can run programs in two ways in Windows, either as console programs or as windowed programs. Windows and consoles have somewhat different functionality, and in my experience, it is more convenient to work with graphics in a windowed program. So that's what we're doing here. In fact, finding out how to make a window, the part we're concerned with right now, is not very difficult. But it is essentially necessary for what we want to do later, so I include it here for convenience's sake. I have included a link to a Stack Overflow article about the difference between WinMain and main functions, if you want to read more about it. The first several lines of the WinMain function are some that I usually just copy and paste from my earlier projects and that I originally got from some Microsoft Docs article about creating Windows or creating your first program. I provided a link to one such article in the description. I don't think it looks exactly like the window we're making here, but you'll recognize most of the things, and it's very useful. After that, we get to a part where we call a function called CreateWindowEx, EX standing for extended. This is where we define a lot of the attributes of our window. And I provided another link to the article about this function specifically. So it allows us to define so-called window styles. This is one. These are another two. There are many more that you can play around with, and you'll find the information about them here, or at least linked from there. This stuff is also stuff I just usually copy and paste. This is, of course, the same variable we defined earlier. This is a new name. You can read more about that in the article. This part is one that I find quite interesting though, and it's very relevant to us. We define the position and the dimensions of our window. The position is of an XY format. The first denotes X coordinate and the second Y coordinate. And X goes from left to right, so 0 means aligned with the left side of the screen. And this 0 means aligned with the top of the screen, because when it comes to computer graphics, the Y-axis usually goes from the top to the bottom, and higher values are closer to the bottom. What these commented out bits are, we will get back to later when we run the program. Finally, there are some lines here that are, most of which are null, as you can see. That means I don't give them any value. You can read more about these as well in the CreateWindowEx article. And it can be interesting to read about these things, but I have yet to make any program that makes use of them. That might be very different for you though. The H instance is a reference to this, which is essentially a handle to the process, so that the window, or so that Windows knows which window belongs to which process. That's very important, obviously. The last part of the WinMain function is a message loop, so-called. So in Windows, a lot of information gets passed back and forth as messages. So for example, when I press a key on my keyboard, Windows picks up on that. It encodes the information about which key it was in a message and sends it to the program that is currently running in focus. So I'm running Microsoft Visual Studio and I have the focus on this window. I have several other programs running, or processes, like several instances of Notebook or Notepad, but they're not in focus, so they don't receive that message. That's when I type here, I'm not typing in those documents as well. This loop consists of 3 functions, one in the while declaration here, get message, and then 2 inside it, translate and dispatch message. Now, I don't know precisely what happens inside of these at all, but I know that in one of them, at least, the window proc function that we defined earlier, or that we declared earlier, gets called. That happens somewhere in here. And this is where the meat of our program should live. Now, our program doesn't do much. It creates a window and it shows a window, and nothing more. So we don't have much code here. And we won't have much code here in this video, actually. But later on, possibly subject of later videos, I will go into detail about how to do different things here. That doesn't mean that all of the program is going to be written in this one file. The usual way to do it is to define some other function elsewhere that you call in here, and in that function then you call further functions that define your program's behavior. To conclude this portion of the window, let's run this program with a few different settings. So let's run it with these settings that we have here. As you see, we get a window that is aligned with the top left corner as per these coordinates, and you can see that it's roughly twice as wide as it is high. Now if we change the coordinates, it should appear further to the left and further down on the screen. And so it does. Now we get to those functions that I spoke of earlier. These are so-called system calls. This one's called getSystemMetrics, and it asks Windows to give us information about our system. And we provide as argument 2 different values here, constants. You can see that they're essentially the same except for this letter, which is X in the first and Y in the second. So this asks for the width of the screen, and this asks for the height of the screen. So what it does, it makes sure that our window has the same proportions as our screen. Now, since the coordinates of the top left corner are not the top left corner of the screen, the window is offset. So we'll fix that. And then you'll see that we have a full screen program. But I haven't programmed an exit button or key, so I have to Alt tab out to Visual Studio and end it like so. Now let's move on to the section where we actually start drawing graphics. I am sure that's what you're most excited about anyway. So here we are at the file that I have provided in the description of this video. It is just over 150 lines, although several of those are taken up by the code that we defined in the previous section. And what it does is it fills the screen with blue pixels and then gives you access to those pixels so that you can start working with graphics. This video is not meant to go into depth about anything having to do with drawing on the screen. It's only meant to get you past the hurdle where you can start working with pixels on the screen. That's what I wanted to do and what I had trouble getting to, and that's what I want to help you with. In the future, I might make more in-depth videos about graphics, but not now. When we get to any part of the code here that I have already discussed, I'm going to skip it, so as to save time. Zooming in, we find some new lines at the beginning of the file. These are some so-called macro definitions that define Unicode. Unicode is a character encoding system. I don't know much about it, nor about macro definitions, so I provided a link to an article that explains them in detail for you in the description. They're not actually necessary to run this program, but they have helped me avoid some really annoying problems in the past, so I think they might do the same for you, hence why they're here. Moving on, past this include, we get to something called an HTC, Handle to Device Context. Here's a very brief, abbreviated definition from Microsoft Docs. What these are, in my understanding, are representations of our output device, so that Windows knows how to draw what we ask it to draw. In our case, of course, the output device is a screen, but it could be something like a printer. And there are many different printers, many different screens, so Windows needs to know the details about the device in order to put any pixels or ink onto it. That's what these do. From my reading, I've learned that this is the representation of the actual device, and this is another virtual device that we have to define and couple with this one in order for the drawing to work. I have no clue why or how that works. Next up is something called a D-word pointer. Now, D-word stands for double word. In programming, a word is usually something of the size 16 bits. And a double word is something of the size 32 bits. That's the same size as a regular integer. Now, this is supposed to work as an unsigned integer. Unsigned meaning that it cannot be negative. And the reason for that is this is a pointer into memory, and those are always positive. And what it does is it points to a memory location, which will be the starting point for our pixel information. So essentially, it's where we keep our image information for the screen. We'll use this every time we draw something. So it's very important. After that, we come to some bitmap information. Now, these are important because in order to draw to the screen via these two device contexts, we need one of several possible tools. I know that there's at least one called a brush, but I went with the bitmap tool because that seemed easiest to me. Now, this is a handle to a bitmap, so it's an access point, you might say. And bitmap info is a so-called header. It's a data struct keeping information about it, so it'll keep information like size and a lot of other things that I actually don't know much about. We'll get to that very soon. Final new thing in this section is a Painstruct. I really don't know much about that at all, but there is a link to an article about it in the description. I think you might recall these from the previous section of the window, at least these two system calls here, where we obtain the width of the screen and the height of the screen. Now, because I'm going to use these values a fair bit more in this program, I'm storing them into integers. It's just much easier to use in the code. And you remember our window proc declaration. And then we get to a completely new bit, a make bitmap function. This is one I've written myself just to contain everything that we need to create a bitmap in one place, so I can call it easier later on. It takes a lot of arguments here. Now, this is essentially the reference to the window program we're running. We're going to need that a lot. So that's why that's included. Then we have the bitmap info header and the handle to a bitmap that I just showed you here. We need them in order to couple the information. When we create the bitmap, we have to couple it with these so that we can get access to it. Then we have the dword pointer, which is the same as this one here. When I call this function later, you will see that I give it all these variables as arguments. You'll notice the 2 stars here. I'm giving this as a double pointer. Now, that's something I won't get into here, but you can read about it in a lot of sources about C or C++ programming. Then I provide width and height, and I will just give this function these 2 variables as arguments, because we need that information. Inside the function, we start by filling in a data struct called the bitmap info header. It's this one we just talked about. Most of these values I am not very familiar with at all. You can infer some of the functions through their names, and they're very easy to find information about. It's just not something that I retain in my head, and it's not very important to me in the work that I do. The first 3, of course, are pretty self-explanatory. These are the dimensions of the bitmap, and this is the size in bytes. This function, size of, can be used in many contexts. It's very useful. Whenever you need the size of something, a struct, a data type, something like that, then you can use this. Very convenient. Next, we actually create the bitmap. This is a so-called device-independent bitmap, which I don't know many details about. It's important that it is device-independent, apparently, for our use. But what's really interesting to us is just that here is where we define the bitmap in question. Now, as you see, that is a reference to this bitmap handle that we looked at before. So now we have an actual bitmap. And we provide it with the information from the header there. And you see that we've coupled it with our window information as well. So this bitmap is connected with our program, so to speak. After that, we use something called getDbits, device independent bitmap bits. These are the bits of the bitmap. So this is the actual memory region where our pixels will live. And therefore we provide the pointer that we spoke of, that I told you was going to be the indicator of where to find our pixels. Also important, and some other information. Finally, we want to fill that memory region with some information. In this case, color information. Now, for reasons that I won't go into detail here, I create a copy of my double word pointer. It is necessary, but it would take time to explain. Next, I just store the size of the screen in pixels in this variable. That's not necessary. I could just put this expression here, and frankly, it would be optimized by the compiler into something very similar to what I've done here. This is just me being explicit. Then I use a for loop, which you're probably familiar with. Now you might be more familiar with for loops that look like this. Oops. With curly braces. Now, if you only perform one operation in your loop, those curly braces are not necessary. It'll be performed anyway. And I think it just looks neat if it's situated right here as an extension on that line. But we'll do this to be explicit. Now what we do is we go through, we start at the beginning of the memory region with all our pixels, and we hop through it one double word at a time, so 32 bits at a time. And at every position, we write a value, an integer value. I have put it here in hexadecimal format just as a small teaching device. Color info is quite often written in hexadecimal, and in this case it is in the ARGB format, standing for alpha RGB. I don't know much about the alpha channel, so-called. I think it has to do with transparency, but I might be wrong about that. The other three, though, are the red, green, and blue components of color, which will together make up the color you have. So every two values here represents one of these here. So the first two represents the alpha channel, next two represents red, these two represent green, and the final two will be blue. And hexadecimal goes from 0 to F. So 2 Fs is the highest it can be, which is 255. That's the highest any component value can be. So we've maxed out the blue, and we put a quite high value for green. So this will be very blue with a slight green tint, but I don't think you'll be able to see the green of it. That's the end of the make bitmap section or function. I have defined another function here called prepare screen, which you'll see me call later on, and in it I'm calling the make bitmap function. And then I'm performing some operations that are needed to actually get an HTC for our HTC variable. Then to create the virtual HTC that we spoke of. And finally, to couple our virtual HTC with our bitmap. So through this chain of system calls, we get a link between our bitmap and our screen. Very important, of course. Then we get to our WinMain function, which is largely the same. I've added some comments. But here, I do call a function called prepare screen. That's the one we just defined. We looked at it here. So that creates our bitmap, and it links everything up for us to use. This is also something that wasn't in the other program. It's not needed here, I'm pretty sure, but let's just leave it in. You might want to use it. I'll probably make videos explaining what it does in the future. And then we have the message loop as before, and then the definition of our window procedure. As you see, we have a bit more information here, a bit more code than last time. We have 3 new functions: bitblit, begin paint, and end paint. So bitblit is a kind of fast memory transfer function. And actually, as far as I know, it uses the GPU to obtain that. We're not using the GPU, the graphics processing unit, for calculations, but we're using it for memory transfer. So once we have finished calculating and drawing everything, we move it to the window, to the screen very fast with this function. That's what it does. It needs to know where to send it though, which window to send it to and in which position. So this function, begin paint, gets access to the window information, our program information, and our Painstruct, and it returns our main device context, if you recall. This one, the one that actually represents the screen. Remember the other one as well, because we provide that too. Because you remember that we coupled this one, the virtual device context with our bitmap. That's how this function knows where to look for the pixels it's supposed to transfer. Then we provide the screen width and screen height because our window is the same size as our screen and our bitmap is the same size as our window. So in order for this function to know how much memory to transfer, we need to tell it. It'll calculate that based on these two. This is a coordinate inside the window. So this is the top left corner of the window. But if the window is not in the top left corner of the screen, then that's not in the top left corner of the screen either. These are apparently coordinates of the original bitmap, and I do not know why they are needed or what they do. But they're there. I've just put them to 0 and that works. Finally, there is an option, which is a kind of drawing option. It tells this function what to do with the pixels when it's transferring them. I know that there are options which will allow you to, for example, mix the pixels, like the ones you're sending, mixing them with the ones that are already in the window. I've not experimented with that because it doesn't interest me, but I'm sure you can have a lot of fun with it if you want to. Finally, we call endPaint, which, in my understanding, this tells Windows that we are ready, that we are finished drawing to the window and that the window is ready to be displayed. And then this, as far as I understand, tells Windows to actually display the window, to redraw it the way we have now modified it. But if we don't call this, whatever you do here is not going to be shown on screen. And that is the end of the code step through. We will now run the program in a few different ways just to demonstrate how it works. So, let's go. Here you see the entire screen filled with blue as predicted. Alt-tab out. And for fun, let's play with those other coordinates here. As I said, these are the coordinates inside the window. This will look a little bit strange now. Now it looks like the window has moved, doesn't it? But in fact it has not. It's because we set WSEX transparent as one of our options or window styles. If we change that to an overlapped window, you will see that it actually does fill the screen, but the coordinate inside the window is different. For a little bit of fun, we can also play with the color information here. Now let's say that we change red to AA and green to FF, and then blue to 0. This should give something yellow, I think. Oh, it's more lime green. I was half right. It's easier to see the cursor on top now, which gives us an opportunity to show this function here, which I think you might find neat. This is how you change whether the cursor should be shown or not. I've set it to false. So you can't see the cursor anymore. That can be useful if you want to do, as I like to do, draw your own cursor. It's still there, it's just that Windows is not drawing the graphic for you. You can provide your own graphic in multiple different ways, as far as I know. We can reset these just to show that works as expected. And indeed. This concludes our video, and I hope it was informational, helpful to you. If you have comments, questions, suggestions for future videos, etc., you can write about those in the comment section, or you can head over to my Twitch channel, which I will link in the description as well. I often sit there and work on my game or on tools for my game, and I'm more than happy to answer questions if I can, and if I can't, there's quite often some people in chat, nice and knowledgeable people, who like to help out when possible. It's also a place where you can share your projects, primarily game related, although they don't have to be code related. They could be music or art, 3D models, sprites, could be ideas for games, anything like that, as long as it's sort of okay according to my guidelines, but you'll find those out if you come to the Twitch channel. No problem. With that, I'll wish you all happy coding and a good day.